In this video, we are going to focus on solving exponential and logarithmic equations. Let's start with exponential. Now, the first two examples are ones that you may have seen in the past. And the way that I look at these problems is I always think about, can I make the bases of these exponential expressions the same? So when I look at the first side, the left side, I look at base 9, and then I'm also looking at base 1/3. When I look at those two values, I notice that those numbers can be rewritten with a base 3. So I'm going to take the 9 and I'm going to write it as 3 squared. And I'm going to put that in parentheses just so I don't lose track of that exponent. On the right side, even though it is a base of 3, the 3 is in the denominator. Well, if I want to raise that base to the numerator, I'm going to write that as 3 to the negative first. Let's clean these exponents up. I'm going to write that as 3 raised to the 2x plus 14 because I'm going to distribute that 2 through, and I'm going to do the same thing here. I'm going to keep that base 3 and I'm going to distribute that negative 1 through. So again, I'm looking at these as binomials. That's going to give me negative 3x plus 1. Now, if you think about that, if I were to look at a much more simple example, if I were to have something like 2 to the x equals 2 to the 4th, well, hopefully you recognize that that x value has to be 4. Because in order for the left and the right side of that equation to be the same, in order for the expressions to be equal, if I were to rewrite this as a 4, I would now have 2 to the 4th equals 2 to the 4th. And we know that those are equal. So I'm going to follow the same strategy. I know my bases are equal. They're both 3. So if the bases are equal, the exponents have to be equal. If the bases are the same, the exponents have to be equal. So I'm going to rewrite this as 2x plus 14 is equal to negative 3x plus 1, and I'm going to add that. Doesn't make a difference what side you get the x to. Let's bring it to the left. If I bring this 3x over, that's going to give me a 5x because I would have added it. And if I bring this 14 over, I would have subtracted that, and that would have given me a negative 13. So now getting that x by itself, divide both sides by the 5, and I end up with x equaling negative 13/5. Let's look at another example. I'm going to now try to make these bases the same as well. Well, when I look at the 25 and the 125, I noticed that I could rewrite both of those bases as a base 5. So let's do that. 25 is the same thing as 5 squared. I write that in parentheses. I'm going to write this binomial in parentheses as well. And 125 is the same thing as 5 cubed with that x plus 4 parentheses. Let's clean up those exponents. So if I have a 5, I'm going to rewrite this combination. I have 2 times this binomial. So that's going to give me 4x minus 2. And on the right, I have base 5. Distributing this 3 as well gives me 3x plus 12. Bases are the same. Let's set those exponents equal. So I have 4x minus 2 is equal to 3x plus 12. I'm going to subtract the 3 over, which is going to give me an x here. And I'm going to add that 2 over, which is going to give me a 14. All right. One more, same strategy. Our goal is to break the bases down so that they are the same. So when I look at the 6 and the 12, well, that gets kind of confusing. There's no way that I can write 6 and 12 with the same base. Well, we just learned a little bit about using a logarithm, and you can use a logarithm when you have a variable that's in the exponent because logs are equal to exponents. I'm going to rewrite this equation in logarithmic form. So my base of my exponential expression is going to be the base of the log. So I'm going to write this as log base 6 of 12 because I know the exponent, that x up here, is always going to go by itself. Now, your instructor may allow you to leave it there. If your teacher says leave it in terms of a log, then you are done. However, if your teacher said, well, I'd like to see that as a decimal value, and I'm sure they'll tell you how many decimal places they'd like to see, you have a couple different options here. Number one, you can use that log base key, which is under that math button. Again, you go to A, and I'm going to put a 6 in and a 12. If not, you can also use that change of base rule. Either way, it gave me 1.3869. Let's look at a couple log solving problems. So I can't make the bases the same and set the exponents equal because I don't even have an exponential equation here. So I'm given a log and I have to find some way to get this x out of the argument. How am I going to get this out of the parentheses? Well, I know that exponential and logarithmic functions are inverses of each other. So let's say I decide to switch this into an exponential equation. Well, my base here is 4. So that 4 is also going to become the base of my exponential expression. Let's switch our forms. This is going to be 4 to the third, or 4 cubed, equals 17x minus 4. Look at that. I don't have any more logs, and I have my x ready to go. So let's solve. I'm going to write 4 cubed as 64. So 64 equals 17x minus 4. I'm going to add 4 to both sides. So that's going to give me 68 equals 17x. And to solve for x, I'm going to divide both sides by 17. Now, that's going to give me an x equal to 4. Well, anytime you're solving log problems, you need to make sure that you check your solution. The values that you have in your argument, or the expressions inside that set of parentheses, always has to be positive to satisfy the domain. If you think about what we got when we were just graphing, a log function looked like this. And that gave us a domain that was greater than 0. So anytime we are solving a function or an equation that has logarithms in it, we need to go through and substitute that value or the solution in and make sure it gives me a positive number. Well, when I do it for this one, if I were to take that 4 and substitute it back in, I end up with 17 times 4, which is 68, and 68 minus 4 gives me a 64. So this expression would really look like log base 4 of 64 equals 3, which again, if we think about it, switching forms again, this would be 4 cubed, which is 64, which we know is correct. Example number 5. All right, well, this is a log problem, and the setup is a little bit different from number 4. So from number 4, I had a single log, a variable in the argument, which I was not quite sure how to get out, so I switched it to an exponential form. But now I have 2 logs that are added together. Well, in our last lesson, when we were talking about the properties of exponents, we practiced writing a sum of logs, which is what you have here, into a single log. So let's try that first. I'm going to take the log base 2, and when I look at my 2 arguments, I have an x and the binomial x minus 2. Now, these are added together. And I'm reminding myself that when I had logs that were added together, or a sum of logs, that creates a product in the argument. So I'm going to write this in one set of parentheses. It is going to be x times the binomial x minus 2. And that's going to be equal to 3. Now, my setup there is very similar to what I had in example number 4. In example number 4, I had one log, a single log, that I switched to exponential. So what did I do in 5? I took those 2 logs and I combined them and wrote it as a single log. Now I'm going to switch it to exponential form. I have my base, which is 2. So I'm going to write this as 2 cubed because I have my base to my exponent. Again, remember logs are always exponents. And that is equal to x times the binomial x minus 2. Now I'm ready to solve. Well, I know 2 cubed is 8, and I know I can distribute this x through, so it's going to give me an x squared minus 2x. I see this leaves me with an x squared or a quadratic, so I'm going to factor to find my two solutions. I'm going to bring that 8 to the right. So that's going to give me a 0 on the left. I have x squared minus 2x minus 8. And I can factor that trinomial. I know you guys are great factors. So that would be x minus 4 and x plus 2. And that's going to leave me with two solutions. The first one is going to be 4, and the second one is going to be 2. Oh, sorry, negative 2. Now, before I decide that I am good to go, I need to remind myself that I have to check my arguments because the value inside the parentheses, or inside, for that example, this x, inside the parentheses here, that x minus 2, and this x need to be positive to satisfy my domain of a log. Well, if I check the positive 4 first, well, if I plug that in, that's going to give me, let's take a look. That's going to give me log base 2 of 4, which I'm okay with. And then it's going to give me plus log base 2 of 4 minus 2, which is 2. Both of my arguments are positive. I can keep on going to check if I choose. Let's do that for this specific problem. So let's say I write that this is equal to 3. I always like to make sure that my answers work. Well, here again I have a sum of logs. And when I have a sum, I can write it as a single log by multiplying those arguments. So if I take the 4 and the 2 and I multiply, it gives me 8. So log base 2 of 8 is equal to 3. Is that true? Absolutely, because we all know that 2 cubed is going to be 8. All right, I'm happy with my 4 solution. Let's go and check negative 2. I'm going to do this a little bit quicker. If I take the negative 2 and I plug it in, here's my first hiccup. If I plug negative 2 into this position here, I'm going to have a negative argument, so that negative 2 is out of there. Okay, one more example. I have 2 logs again. Well, I really liked how I approached number 4 and 5 because I was able to combine the logs to get a single log. And again, this is something that I'm recognizing that I could do because here this 2 doesn't have a log. Up here this 3 didn't have a log. And the problem before, number 4, this 3 didn't have a log. So for each one of those problems, I had one value without a log. All right, let's do this the same way I did number 5. I'm going to get that value, that 2 by itself. So now it looks like the other problems did. So I'm going to write this as equal to a 2. I'm going to subtract this log, and there's no base, which means it's base 10, a common log. So I'm going to subtract that log to the left-hand side. So now I have log base 10 of 5x minus 1 minus log base 10 of x minus 2. To write that as a single log, since these are subtracted, it's a difference of logs, I'm going to use division. Now, if you'd like to write the base 10, you can. If you don't, then leave it out. The first argument, that 5x minus 1, that's going to go in the numerator. And the second argument, that x minus 2, is going to go in the denominator. And now that's equal to 2. I wrote it as a single log. Let's switch it to exponential. That's going to give me 10 to the second is equal to 5x minus 1 over x minus 2. Now this is over 1. I know that 10 squared is 100. So if I cross multiply here, that's going to give me 100 times x minus 2. And this 1 times 5x minus 1 is not going to change. Let's keep going. I have 100x minus 200 is equal to 5x minus 1. All right, a couple more steps. If I subtract the 5x over to the left, that's going to allow me to add the 200 to the right. So 100 minus 5 is going to give me a 95. So I have a 95x is equal to negative 1 plus 100 is negative, positive 199. And so to finish that problem up, I'm going to get my x by itself, and I'm going to do that by dividing both sides by 95. So that's going to leave me with my final answer of 199 divided by 95. Now, if you look at these last two examples, they don't have the same form as my others did. And the reason I'm saying that is when I analyzed the setup, the other three examples that we looked at each had a value or a number that was not attached to a log. And that is not the case with 7 and 8. So we're going to approach these in a different way. Now, if you think about how we did those exponential expressions, when we solved those exponential equations, we said if you can make the bases the same, then you can set the exponents equal. And I'm going to follow a similar approach. For these, I'm going to try to make each one a single log. So if you have a single log with the same base, so it's going to be in that log equals log setup, then you can set the arguments equal. And we're going to expand that a little bit as we work through these examples. Okay, now I'm going to try to write it as a single log equals a single log. So I'm happy with the right side here because the right side of number 7 is log base 4 of 25. There's no coefficients for my log, so I have my single log. But on the left-hand side, I do not have my log alone. I have a coefficient, and this coefficient I need to bring up to become an exponent. So again, when we were working with our log properties in the last unit, your single log had to be one large argument with possibly products and quotients and powers, but no leading coefficient. All right, so I have log base 4 equals log base 4. For these expressions to equal, if we think about it, it would only make sense that this has to equal 25 for the left and the right to be equal. So let's do that. I'm going to set the binomial x plus 3 squared equals 25, and I'm going to solve it. Well, there's two different ways you can do it. You can take the x plus 3, write it twice, multiply it out, and bring the 25 over. But I also recognize that if I have a binomial squared, I really can just take the square root of both sides because I'm recognizing that that 5 is a perfect square. Now, I know I have to have two solutions, so this is going to be x plus 3 equals both 5 and negative 5, so plus or minus 5. Solving those two cases, I'm going to have an x plus 3 equals a positive 5, and I'm going to have an x plus 3 equals a negative 5. So that's going to give me an x is equal to 2 as one solution, and it's going to give me an x equals negative 8 as my other. Similar to the other problems, we need to check those solutions to make sure that the argument is positive. And again, one more reminder why that is true is our log graph looked like this. That was my vertical asymptote, my y-axis. And I know that in order for this function to be true, it has to have a domain that is positive. The domain had to be larger than 0. All right, so let's check these values. Positive 2, if I plug it in here, is fine because 2 plus 3 gives me 5, and that's positive. Good to go. Negative 8, when I plug in here, ooh, that doesn't work because negative 8 plus 3 gives me a negative 5. So, sorry, negative 8, you are gone. My only answer is positive 2. Why don't you pause the video and see if you can solve number 8 on your own. Okay, hopefully you took the time to do it and didn't just wait for me to come back. I'm going to approach it the same way I did number 7. All right, I'm thinking I'm going to write this as a log equals log. However, when I look at the setup on the left, I don't have a single log. Well, that's going to require me to do a little bit of work. Let's combine these two logs to be a single log. So since there is a sum, this is an addition, I know I'm going to write it as a product. So that means I have log base 2, in parentheses, I'm going to have x times the binomial x minus 6, and that's going to be equal to log base 2 of 2x minus 7. Now, if I have two logs with the same bases that are equal, the only way that that makes sense is that the arguments are equal as well. So I'm going to set that x times the binomial x minus 6 equal to the binomial 2x minus 7, and I am going to solve. X squared minus 6x equals 2x minus 7. Bringing that 2x over is going to leave me with a negative 8x, and I'm going to add that 7 over as well. You guys are great factors. That's going to give me an x minus 7 and an x minus 1. So I'm going to have two solutions again. Super exciting. I have positive 7 and positive 1. Not sure they're both going to work. Let's do a quick check. Does it make sense that 7 works? Well, if I plug 7 in here, it gives me 7. That's good to go. If I plug 7 in here, 7 minus 6 is 1. That's good as well because it's positive. And if I plug the 7 in here, that's going to give me 14 minus 7, which is 7. Boom. So the 7 works. It creates positive arguments. Let's try that 1. Well, if I plug 1 into this x, that's fine. It's positive. If I plug 1, oh man, this is where it falls apart. 1 minus 6 would give me a negative 5. Falls apart again here too. If you were to plug a 1 in here, this is going to give me 2 minus 7. That's negative as well. And that 1 is out. Now, sometimes none of the solutions work. Sometimes they both work. In these two examples, you only had one for each problem.